Yeah, first I want to express my thanks, my gratitude for letting me speak here tonight. Actually, it's morning where you are. And I'm going to talk about embedded systems. And I will also provide some information about the work environment of an embedded systems developer in case any students want to take up that direction of work. I want to provide an overview over the upcoming embedded systems course. And yes, at the end of the presentation, provided there is time, I intend to talk about 2 examples of embedded systems implementations from my previous work experience. Okay, next slide, please. Okay, I'm starting first with the question, what is an embedded system? In short, it is basically any computer system that isn't a general purpose computer and was designed or configured for a specific purpose. An ordinary PC can become an embedded system if you take it away from someone's desk and put it in a box and use it, for example, to show a selectable store directory in a mall. Embedded systems are the vast majority of computer systems around us. Every time you see a device with a display or flashing lights or sensor inputs or any kinds of smarts, there's most likely a microprocessor inside. On this slide, there are some examples of embedded systems and where they are used. Usually, I've grouped it into commercial, industrial, agricultural, transportation, and military. And this is not by coincidence. It roughly also is connected to the temperature ranges of the components that are being used in these devices. And it is also the approximate order in which programming errors become more and more critical. When you walk into your house and you have a reasonably modern kitchen, you're most likely surrounded by dozens of embedded systems in toaster ovens, in wireless barbecue thermometers, in microwaves. In this case, on the list here, dishwashers, laundry machines, and so on. Industrial applications, remote sensors, basically sensors that are sensing pressure or temperature, for example, but are connected over several kilometer-long cables. Those will have embedded systems inside. Process controllers, motor control, power conditioning, and so on. Agriculture, irrigation systems, environmental sensors. So basically sensors that can tell you when irrigation is supposed to happen. Transportation, the most obvious example is engine control units, but also brake controllers and, for example, on trains, passenger information systems. Military, just guidance systems, shell fuses with inertial triggers, for example, drones, autonomous vehicles, for example, for demining. Okay, thank you for switching over. I just wanted to, for the previous slide, I just wanted to quickly point out the topics that I started about the programming errors. Usually in programming errors in the different sections. Can I see the previous slide again? Sorry. Yeah, okay. Just a very quick talk about the safety and programming issues. In commercial and consumer goods, programming errors or mistakes are usually not critical. They incur financial loss for the company. Most or the worst usually that happens is that a product recall is happening. But generally, the hardware is configured in a way that a programming error doesn't create any deadly problems. And industrial applications are different. Industrial applications, programming errors might have as a consequence injury or death. The same in transportation. Obviously, if, for example, a brake controller doesn't work in a car or the train, that can lead to a mass casualty event. And the military, of course, as well, the devices themselves are often designed to be destructive. And so programming errors can have severe consequences here as well. So depending on the field that you would be going into, if you're interested in embedded systems, the further down the list you go, the more stringent the safety requirements and the programming safety becomes. Okay, thank you. Next slide, please. Okay, I have a list here that may just list like a random list of items, and it might not even be complete, but there's a reason for this list. If you work as an embedded systems developer, and I just wanted to quickly discuss the relationships between these items and the consequences. Price and volume is obvious. The more components your company buys, the cheaper the components become. It's just volume discounts. The higher the production numbers, the more support and attention you will get from distributors and manufacturers. If you're participating in the development of a product, the support of your suppliers is very important, either from your distributor or from the actual manufacturer. Generally, if you're designing a product that is supposed to be sold in numbers of more than about 1,000 pieces a year, the distributors will come by and you will get attention. In more extreme cases, if your product is, for example, selling more than 1 million pieces a year, the manufacturer will pay you a lot of attention, and up to the point where they will provide their own engineers for solving some of your problems. I was in a engine control unit project at some point in the past, and this control unit was supposed to be reused in a number of vehicles, and the manufacturer of a specific microcontroller that was only supposed to be doing kind of like a side job, a small function that was not the main function of the engine control unit. But the manufacturer was basically supplying engineers to solve this problem, just so that they could get their product or their component, their microcontroller, into the device. As a developer, the higher the production numbers, the more pressure there will be to replace hardware with software. So if you're designing firmware, then you possibly have to be prepared that your boss, the product manager or project manager, will try to get you to replace hardware with software, to basically write software workarounds to save a few resistors or a transistor or like a logic circuit. So that is also an item that might come in commercial in development for commercial devices. Industrial and agricultural devices usually have lower numbers, lower production numbers. And very often in these situations, it is the time to market is more important. And so the devices can be, or you will have a wider selection of components that are available to you. One quick example that I wanted to bring, sometimes there is pressure to implement solutions that don't really work. I have an example here. For example, in one product that I was working on, there was a ground fault monitor supposed to be implemented. And the ground fault monitor had two displays. One display was basically an array of LEDs. They were connected to comparators. And another display was in software on a screen. And the company was basically trying to avoid hooking up all the comparators to the microprocessor, and was basically just attaching an A to D converter to the ground fault measurement to measure the severity of the ground fault. The circuit worked perfectly. The problem was that you could never quite exactly hit the threshold at which the hardware comparators for the outside LEDs were running. So in testing, there was always a situation where the test personnel was able to indicate a certain amount of ground fault, and the software would show a different amount of ground fault because of the tolerances in components. So sometimes the pressure of trying to save components will create problems for the developer that need to be addressed right away. Okay, component availability. That's pretty simple. The best suited microcontroller or component might not be the one that is available at the distributor. You might have to work with a barely suitable device simply because it is available, or the company has it in stock for use in other products. Sometimes the company where you work will also have to determine what you can use in your projects simply because it is in their ERP system. If somebody doesn't know what ERP system stands for, it's Enterprise Resource Planning. Time to market. How long will it take? What does it mean? It means how long will it take to develop for this microcontroller until the product is in production? It means how much sample code and libraries are available. How good is the manufacturer documentation? How good is the development environment? How difficult is it to prototype? What are the package options? Are there demonstration boards available? If the development time is short, an SOM module, like a SOM module, which is a system on module, is sometimes the easiest way out, even if it is more expensive. Product longevity. This doesn't refer to the reliability of the product. It means how long will the components that you're using be available for sale? How long are you trying to sell the product for? Some manufacturers will give you lifespan guarantees. A long lifespan and support requirement for your product might radically alter the hardware that you as a developer can work with. If your company plans to produce a product for decades, then the latest technology might not be the technology to use. And transistor circuits, for example, might be used over integrated solutions, even if it is more expensive and larger. Product reliability. Components age and drift. Some products have a limited design lifespan. Some must run forever, especially in industrial and transportation. You might have to implement code to self-calibrate and compensate for product aging. Product support. Especially industrial embedded systems products, less so commercial, might run for decades and will need to receive regular or irregular updates. And what that means for you as a developer is you have to write your software in a way that you yourself will be able to understand it. Even a long time later, even after 10 years, your product might run perfectly for 5 or 10 years, and suddenly your company boss or your project manager comes back to you and says, okay, we need an update for this. So when you're programming, always program in a way that you understand your own code 10 years later. And of course, write it in a way that another programmer, like assuming you have left the company, for example, write your code in a way that another programmer can pick up right where you've left off. That is much more important than people give it credit for. Documentation is key. Ease of use and customer training. Consider your target audience. Who will be using the product? Will there be training? For a commercial product, there will be no training. For an industrial product, your company might provide training. So the user interface can be more complicated. On the other hand, if your company is providing training, this is adding cost to the product. And if you can make the product simpler so that it can shorten the time of the training, you can save your company some time. Okay, next slide, please. Hardware. In the next section, we're going to talk a little bit about the hardware for embedded systems. Next slide, please. Embedded system hardware can be generally grouped into 3 categories: microcontroller-based, using real-time operating systems or no operating system, single-board computers, or embedded PCs. The course will briefly discuss these issues, these items, or the differences between these categories and the use cases, and then switch to focusing on microcontrollers. So I just wanted to talk a little bit about, because we will be focusing on microcontrollers, about the single board computers and the embedded PCs. Another item is, what I didn't put in this list, is FPGAs. That is kind of a different category just by itself, but you can build embedded systems with FPGAs alone. If somebody does not know what FPGAs are, those are programmable logic devices that can contain basically a microcontroller core and are therefore programmable as well. Or not even just a microcontroller core, they can contain a full processor core. So quickly focusing on the single board computers. What is a single board computer? For example, a Raspberry Pi. Everybody most likely will have heard of a Raspberry Pi. Is a single board computer. It is generally designed to run, like a single board computer is generally designed to run a full multitasking, multi-user operating system. The processor, RAM, and non-volatile memory, so the program storage, are in separate components on one board. It is all soldered fixed onto one single circuit board. It lacks the expandability of a PC, but it can run similar operating systems. Most single board computers nowadays run a derivative of an ARM Cortex-A microprocessor, sometimes Intel, but then you're slowly getting into the realm of embedded PCs. Embedded PCs are basically just normal PCs, but rugged. Or most of the time, they're being put into a rugged industrial or industrial enclosure. Most of the time fanless, and with an expanded temperature range. And often they contain PC untypical interfaces, for example, RS-45 or CAN, in addition to Ethernet. They have better expandability than single board computers, but limited compared to regular PCs. For example, regular PCs have PCI Express slots. Embedded PCs usually only have either 1 or 2 or none. So why aren't we using embedded PCs for everything? Because every embedded PCs have like easy programming support, lots of off-the-shelf parts, lots of processing power. And the answer here is it's related to price, power consumption, and real-time capability. When I'm talking about power consumption, just as an example, a microcontroller can do something useful on a few microamps. Like 200 microamps, and you can permanently run a microcontroller and have it check a sensor. A single board computer, like a Raspberry Pi, for example, can run at 200 milliamps if you, like in full or in running mode, not in sleep, in running mode. A full Raspberry Pi uses up to 2 amps at 5 volts. An embedded PC might use up to 10 times of that. Some of the more modern embedded PCs do have a fairly low power consumption that approaches the power consumption of single board computers. But generally, an embedded PC is always a high power implementation of an embedded system. So it is not really suitable to use an embedded PC for battery-powered applications. In addition to that, Linux and Windows are not real-time capable operating systems. What does this mean? They're not designed to provide responses within definable timeframes 100% of the time. For example, an engine controller that is designed to provide ignition timing. It has to provide a proper, accurate ignition timing 1,000,000 times a month. And this cannot be running on Windows or Linux even, because 99.9999% of the time, Linux might meet the timing requirements, but the one time that it doesn't might destroy the engine. So when I'm talking about a real-time capable, it has nothing to do with a real-time clock. It has everything to do with responding to external events within a definable time frame. What are the advantages of embedded PCs and single-board computers? When are they being used? They're often being used for example, human-machine interfaces. Often, microcontroller circuits and single-board computers or embedded PCs are being combined. So the microcontroller is measuring in is providing real-time capability. The single-board computer or the embedded PC is providing a human-machine interface. So it can run a display, it provides USB support, it provides TCP/IP connectivity, for example, Ethernet connectivity. So in those situations, multiple computer systems or multiple embedded systems are being integrated into one larger embedded system. Okay, next slide, please. The course will then focus on microcontroller embedded software development without an RTOS, bare metal. That is called bare metal programming. A microcontroller is a small computer system on a chip containing the central processing unit, RAM, NVM, non-volatile memory for program storage, and many on-chip peripherals for specific tasks and interfacing with off-chip hardware. And what I had mentioned before, in practice, an embedded system product may consist of several microcontroller circuits and or single-board computers. It is actually now also common for the processors in single-board computers to contain multiple cores of different types. Some of the newer microprocessors contain inside the microprocessor a core for a microcontroller. That happens for exactly that reason, for real-time operation, to separate those two issues. Microcontrollers are common components, can be purchased from many distributors. They're cheap, they're available in vastly different performances and capabilities. You can buy them from 50 cents to $20. So microcontrollers are absolutely accessible for the hobbyist. And a lot of you might already be working with hobby microcontrollers. People might have heard of Arduino microcontroller boards. They are very popular. The course is intended to give an introduction to the building blocks of an embedded application and an introduction to the typical hardware interfaces of a microcontroller. Including RTOS, real-time operating system, handling would exceed the format of the course, but if you're interested in it, please talk to your professor. I'm sure there can be something arranged. Bare metal programming does allow you to keep complete control over the microcontroller, over the microcontroller processor core and the timing. Basically, when you're doing bare metal programming, the developer controls the entirety of the microcontroller's behavior. This will be discussed in the course. Okay, next slide, please. However, there are a wide variety of microcontrollers available on the market. The practical work sections of this course will be based on the STM32L432. It's a modern device using a 32-bit Cortex-M4 ARM core. If somebody doesn't know how the ARM cores work, the company ARM is licensing their core designs to the actual manufacturers. So in this case, ST Microelectronics is producing the microcontrollers using this core, but there are other companies, like for example NXP, who are also producing and selling microcontrollers with the exact same core. These companies have, of course, different microcontroller peripherals, but the programming of these is very similar, and very often the same compiler is being used. Not the same development environment, but the same compiler. Like behind each individual development environment from each manufacturer, essentially very often is the same compiler, which is kind of funny. Compared to PCs, microcontrollers have very limited memory and processing resources, are low cost and low power. I mentioned the low power part. Microcontrollers typically interact directly with external hardware to solve a specific problem or task. Traditionally, embedded systems programming teaching starts with using 8-bit microcontrollers. I've mentioned the Arduino family. We will be later seeing a project that was done with a microchip PIC18F family, which is also an 8-bit microcontroller. However, the 32-bit Cortex-M family has become so inexpensive and well supported, and most importantly, they are price competitive with 8-bit devices at an immensely higher performance. So in this case, we decided to start right away with a 32-bit microcontroller. You might, if you're working in the field of embedded systems, you might very likely still encounter and need to program 8-bit microcontrollers. So the course will address like some simple software techniques for very low memory and pin count microcontrollers and mention avoidable bugs or bug causes on 8-bit devices, which is usually related to interrupts and non-atomic instructions. If somebody doesn't know what non-atomic instructions are, it means in this case non-divisible, or it has nothing to do with atomic power. It is meant to indicate that, for example, a pointer update of a 16-bit pointer has to be done in 2 write cycles. If an interrupt happens within these 2 write cycles, there's a problem, or there can be a problem if in the interrupt the same pointer is being used. So using a 32-bit microcontroller avoids all of these problems right from the start. A Cortex-M4 microcontroller can easily achieve response times in microsecond timeframes. These microcontrollers run generally in the tens of megahertz up to 100, 150 megahertz of clock frequencies. So they can be made to run, to work on tasks that are very, very time sensitive. Next slide, please. Embedded systems developer works at the intersection between hardware and embedded software and application software. What do I mean with intersection here? As an embedded systems developer, you will need to know the devices you're working with, the capabilities and pinouts of microcontrollers. You will need to read data sheets and errata sheets. And for example, you will need to be able to recommend a device for a specific project to management. When you're at the intersection of these different disciplines, hardware and application software, it means you might need to work directly with the hardware development team and support their design and prototyping process. For example, if the task is to measure a signal frequency or a pulse width, or measure a quadrature signal, you don't need to know what a quadrature signal is, but it requires a special peripheral on the microcontroller. Then the firmware designer will have to advise the hardware developer which processor pins are suitable for the task. You might need to prototype the circuit yourself first to make sure that it actually works before telling the hardware designer that he can go ahead with using those pins. The developer will need a basic understanding of the connected hardware. And yes, you will be directly involved in supporting hardware development. Yeah, last point for later. Once a circuit is designed and in production, the embedded systems developer might need to support the hardware developer with custom firmware for circuit testing. So, for example, if the hardware developer has created a circuit that needs a pulse or a pulse train from one of the processor pins, then he stops testing there and he's going to ask you as a developer, okay, can you write me a firmware that can provide this pulse train on this pin so that I can test my hardware? So there will be most likely a very close working together with the hardware department. Sometimes, if you're becoming more advanced, in particularly difficult circumstances, when debugging sporadic failures, it becomes a task of the firmware developer to debug hardware problems. Because you as a firmware developer, you will have the capability in your hands to log sporadic component failures. Like you can log it if you have a memory available, some kind of micro SD card or so that you can access, then you can log the data that is being needed for the hardware needed by the hardware designers to fix their hardware problem. Sometimes you will be the first one to see these problems when your firmware is showing sporadic errors that are being caused by components that are out of tolerance or insufficiently specified. In particular, for example, ceramic capacitors are terrible at this in terms of tolerances and or transistor gain at the temperature extremes. On the other end of this, you might need to talk to the application software developers. If you're working on an embedded system that has both microcontroller and an embedded PC, the embedded PC most likely will be presenting the data to the user and possibly store data in a database. And you will have to provide data to the application software well enough that it can fit properly into that database. So an understanding of application programming and database structures might also be of advantage in those situations. This will not be asked for from you if you're a beginner, but sooner or later this might happen. You will also have to understand on the PC side that the Windows or Linux operating systems have limitations in terms of data might get requested. You might be offering data on a bus to the embedded PC, and the data might get requested or picked up in regular intervals most of the time. And then sometimes the PC just hangs. And the data will not get picked up. And your firmware will have to deal with not creating a buffer overflow, for example, if that happens, and either discards the data or indicates that a problem has happened. Often, you will have to write or participate in the writing of APIs, application programmers interfaces, related to the application software. And you will need to understand and agree with it and implement it. The last item here on the slide is, unlike PC software, microcontroller software is typically cross-compiled and transferred into its target system by the use of an additional hardware device programmer. You can see, for example, an example of these programmers in the little pictures at the top right of the slide. That is in particular the ST-Link V2 and the ST-Link V3. If you're ordering microcontrollers from places like AliExpress or distributors, they might have different compatible programmers, and they usually work. Just in case, if you want to experiment yourself, the STM32 microcontrollers are available on these websites as well if you just do a search for specific ones. I'm sure you will find the STM32-103, the F103, the F401, L401, F411. You will find a lot of demonstration boards with these specific microcontrollers, like on these distributor sites. Okay, next slide, please. Okay, we're going to talk about the software and tools to be used for the embedded systems course. Next slide, please. Okay, the Kharkiv Embedded Systems course uses the STM32 Cube IDE, a software development platform for code examples and practical work. The STM32 Cube IDE is a manufacturer-supported development environment for Cortex-M microcontrollers. The Cortex-M microcontroller line, by the way, consists of a number of different types of cores. We are going to use the L4 core. There's a number of lower performance and cheaper and low power, or also higher performance cores available. The STM32 Cube IDE is Eclipse-based. Eclipse is a popular development environment that is being used by a number, it's open source, that is being used by a number of development environments. It has some strange peculiarities, specialties, and we will be explaining how to use it in the course. Your professors will be explaining how to use it in the course. The specific item here for the STM32 Cube IDE is the code generator. Because the powerful 32-bit microcontrollers, the Cortex-M microcontrollers, have become very complex to set up for the initial project setup. In the Cube IDE, a code generator is provided. That means you can configure your project graphically on screen, and then you can basically click on Save, and you will get a whole bunch of initialization code ready provided for you to use. That is a feature that will save an immense amount of time when you're designing projects. The programming language for the course software and examples and exercises is C. Most of embedded systems projects are written in C. The language has advantages and disadvantages. It gives you a lot of power about how to use the microcontroller, about using even very specific peripherals and features of the microcontroller. You're in full control. It also has the problem that it is very easy to create bugs. So we will probably talk later about alternatives to C, but at the moment, C is in most cases the language of choice for microcontroller development. C++ as well, but C++ requires a lot of processing resources and has other issues that we are going to talk about in the next slide, I believe. Some more items about the Cube IDE. The Cube IDE is free, can be downloaded by anyone. So anyone who wants to use this as a hobby can download it and use it in their own projects. It contains the standard proven GCC compiler core for the Cortex-M family. There are several alternative development environments available. Popular ones, for example, are IAR and Kyle. but these often have a significant cost, several $1,000s. You might want to ask, here's a free development environment, which is really good, actually. Why would anybody pay money to buy something different? This is partially related to legacy reasons. A company that has been using Kyle or IAR compilers for a long time will not switch just because something free just showed up. It is also sometimes being purchased, the SoftDZ programming software, the IDEs, are sometimes being purchased for liability and support reasons. This may sound weird, but sometimes a company insists on paying for a product because the legal department wants something or wants someone to sue if something goes wrong. It is not unusual, and for example, there are RTOSes, for example, free RTOS, which are free, but they do provide a paid-for alternative, which is basically exactly identical for companies who absolutely want to spend money on a product that could be free. Yes, that happens. Another item, of course, is support. Like if they pay money for a product, they're entitled to support. The code generator immensely reduces the work. I mentioned that. And the C++ programming, just wanted to mention the performance penalty and resource use, especially when you're using actual object-oriented features, is severe. The STM32 as a 32-bit microcontroller does have the resources most of the time to do this. Very often, the application of an embedded system prohibits the use of these object-oriented features because most of the time they use dynamically allocated memory on stack and heap. And in many applications, this is simply not practical because the question is, what happens if the system runs out of memory? A PC can simply throw up a message and saying, I'm out of memory, buy me more memory. An embedded system cannot do that. It has to continue to work. An engine controller cannot suddenly say, I'm out of memory, and stop the engine. So very often you might work on applications where every bit of memory has to be accounted for. Every variable has to have a place where it goes. And no malloc memory allocation commands in C are permitted. Okay, next slide, please. This is an example screenshot of the graphical configuration utility for an STM32 microcontroller. It is not the one that is being used in the hardware for the embedded systems course, which will be simpler. It is complicated, not as many pins as this one, but this is an example of a view that you would be seeing when you configure your project. You can essentially click on the pins. You can decide what feature you want on these pins to show up, if it is just a regular input-output, if it is connected to an interface, if it is connected to a PWM output. We will, or your professors will explain during the course what each feature does, or probably not all of them, but the ones that are being handled in the course, and will guide you through this configuration process. This is easy. If you were to click on the clock configuration tab, if you look a little bit higher up, you're at the moment in the pinout and configuration tab. The clock configuration tab looks extremely complicated. It does not need to worry you when you get to that point. Okay, next slide, please. This is a screenshot of the STM32Cube IDE in C++ editing view. Also, you will not be using all of the different features, all of the different windows, but at the minimum, you are going to use the project view, the project file view in the upper left, and of course, the editing window. You will also go into the debugging view at some point in time, but this will all be part of the course. And it is relatively simple once it is understood how this is being handled. This is typical for an Eclipse-based development environment. You might have seen that in other development environments as well. Next slide, please. C is the programming language for the majority of microcontroller-based embedded systems projects. I had mentioned that before. Microcontroller software can be in active use for many years, maybe ported to other microcontrollers of the lifetime of a product. Other products may require safety integrity level certification. That is a thing. And I will talk a little bit about that later. For this reason, the course will briefly discuss coding standards and version control systems to aid in reuse and certification of product software. It is simply something that when you work in the industry, if you get to a company, most likely they will have processes for that. Small startups, like 5-10 people companies, might not. But once a company has a certain amount of product that they're selling, once a company has a certain amount of developers, coding standards are just simply something that is absolutely necessary. C is a double-edged sword. I mentioned that it allows for total control over the microcontroller and maximum programming efficiency. It can also lead to very hard to find and hidden bugs in obfuscated code. And my response to that will always be document your code. When you're writing code, document. Because at worst, 10 years later, you will have to look at your own code and have to figure out what did I do 10 years ago. Alternatives are available to C. Alternatives to C are available, but they're not very well supported as of yet. For example, people might have heard of Rust. There are some embedded systems that are being programmed in scripting languages, for example, Python. But those are rare and usually only for beginners because they are simply not efficient. An interpreted language can never be as efficient as a compiled language. Pretty much every company has coding standards. Sometimes they're just a collection of syntax requirements. Sometimes the code has to pass like a tool like PC-Lint, and that is their coding standard. And sometimes they're following official coding standards, which exist. For example, for the automotive industry, there is a standard called MISRA C. And that coding standard is intense. If you find a MISRA C checker and you basically run a regular embedded systems product or program through a MISRA C checker that has not been programmed to be compatible to MISRA C, they will complain about hundreds and hundreds of items. Like the checker will complain about hundreds and hundreds of items. It does lead to very, very clean code though. So it is a very good tool. It is, of course, not free. But you might encounter this in companies that do write software, that do create embedded systems for safety critical devices. In some companies, the entire development process has to follow standards. In this case, for example, there's a standard, a European standard, the EN 50128. Which is a standard that includes instructions for how the software has to be developed. It includes rules, how documentation has to be written. It includes rules who can test. For example, the person who's writing the code cannot test his own code, his or her own code. And this is for applications that are for the higher or highest safety levels. most of the time, in industrial applications, for example, if it gets to the highest safety levels, instead of implementing these development processes, they just change how the process control works. It is simply easier to make it safer, so that a software bug can't have severe consequences. Okay, next slide, please. Okay, the course will also contain programming of peripheral modules within a microcontroller, GPIO, timers, related to timers, of course, PWM, A to D converters, serial interfaces, some software techniques for resource-constrained microcontroller systems, problem-solving approaches for common embedded systems tasks, for example, state machines. This is all normal items in a microcontroller that need to be in a course like this, especially items like GPIO and state machines. That's how it starts. Related to this, the course will go a little bit in detail about, for example, related to GPIO and PWM, low side, high side, full bridge driver hardware, and the associated features within the microcontroller peripherals. And for example, fault modes. What happens if you can you detect a line break? Can you detect a short to ground? Can you detect a short to VCC, to your power supply, and so on, before something bad happens? Also, the peripherals, for example, in your microcontroller will contain features that allow you to control real-life switching hardware. For example, little delays between switching between upper and lower switches or MOSFETs within bridge drivers. Not in extensive detail, but just to mention that these features exist. The course will also target the most common serial interfaces for onboard and offboard communication between peripherals and external modules. When I'm making a difference here between onboard and offboard communication, the onboard communication, for example, would be interfaces like I2C, like SPI interfaces, which are designed to interface to components that are on the same circuit board. And offboard, that would be interfaces like, for example, CAN bus, Ethernet, RS485, that are more fault tolerant and that are designed to connect to off-board devices, for example, to a embedded PC. Resource-constrained system is a fancy way of saying that there is very little memory size and processor speed available if you compare it to, for example, larger microcontrollers or embedded PCs. So the memory sizes here are given in kilobytes, not megabytes, not gigabytes, but kilobytes, sometimes in bytes. It is entirely possible and viable for a microcontroller to have a memory amount of, for example, 64 bytes. And these are being used. For example, if you write a product that has that is controlling, or if you write firmware for a product that is controlling a few flashing lights for a toy, that doesn't need a 32-bit microcontroller. That doesn't need megabytes of memory. Yes, 64 bytes is enough. State machines are important because they're typically your first working approach to a solution. Sometimes they're not efficient, but they usually lead to a working solution. And after that, you can try to make it more efficient. Especially in bare metal programming, where you don't have an RTOS, you will very likely be using several nested state machines to solve a specific task or problem with your embedded system. Many different state machine implementations exist. Pretty much every programmer, every person has their own preferred way of implementing a state machine. Your professors will try to teach you a state machine structure that will be fairly universal, and will work for you and for the experiments and for the lab work that you'll have to do. But don't be surprised if you will encounter strange or unusual implementations of state machines in legacy code if you start working as an embedded systems developer at a company and you will have to look at other people's code. Sometimes people have made really weird state machines that I've seen where they created what's called a state explosion. Where they were trying to be really, really thorough and created way too many states than necessary. Next slide, please. The next section will give a short description of the laboratory boards for student use. Students will be given specific exercises to be completed within these boards, but they can be used for a number of different experiments or tasks. The board design is open source if the university will make them open source. If students are interested in building some of these boards for their own experiments, I believe that can be permitted or organized by your professors. That is up to your professors. Next slide, please, and question. Do we have reached the break time, or should I continue?
Шановні студенти, Фолькер питає, чи нам потрібна перерва зараз, чи він може продовжувати?
Мабуть, ні.
Потрібно.
Дякую. Dear Volker, you can continue without any interrupting. Thank you.
Oh, okay. I hope enough people can understand me, but I'm sure somebody hopefully will translate what I'm saying. And I hope my English is well enough. English is not my first language, so I've been living in Canada for a while, so I hope it's good enough.
Yes, we understand.
Yeah, we understand it.
Okay, great. Thank you.
It's understandable. It's okay.
Okay, great. Okay, we are on page 16. The student will work on hardware that was developed for a wide variety of student experiments. Here's a quick picture of the board. This is called the STM32L432 Nucleo board. It's a development board. We designed a custom carrier board for this. This Nucleo development board is available. It's a low-cost board. Here in Canada, it costs about $15 from a distributor. It is manufactured by ST Microelectronics, basically by the processor manufacturer themselves. So this avoids the possibility of fake components. It is kinda not a good idea to design like an official university project based on stuff from AliExpress, because you never know what you're getting there. The components can be fake. The nuclear boards, when they're coming from an actual distributor, they are definitely not fake components. Students can purchase the Nucleo boards from the whatever distributor is available. I know that DigiKey has a presence in Poland. But Europe has a number of other companies that are selling these. I know of the ones in Germany, for example, Reichelt Elektronik in Germany. They carry these. But otherwise, these boards are available to everyone, and schematics and support is provided by ST Microelectronics. All Nucleo prototype boards contain their own programming hardware. That is a big advantage. Essentially, every Nucleo board contains a built-in ST-Link V2. In larger Nucleo boards, not the one that is being used here, but the larger ones, this programming hardware can be separated and operated independently as a programmer. You will see, like on these boards, if you look them up, you will see kind of like a break-off capability. The circuit board has slots, it's slotted, and it has break-off locations. That means if you, for whatever reason, you decide that you don't want to use this Nucleo board anymore, maybe you have exhausted the flash memory rewritability of the microcontroller, you can break it off and you can use that part as an independent programmer, like the leftover part as an independent programmer. On the other hand, the original Stealing V2 and V3 are inexpensive as well. There is really no shortage of options to use the ST microelectronics microcontrollers. There are a lot, I find they're a lot more accessible compared to, for example, NXP devices. Okay, next slide, please. Oh, sorry. Maybe a quick step back. I haven't actually addressed the bottom part here. So this board does not have too many available pins. It is a fairly low pin count microcontroller. However, the development board, the lab experiment board, has tried to make as many of these pins available for specific tasks for building the highest amount of possible, or for designing the highest amount of possible lab experiments. In this case, it is designed, you can switch relays, you can switch motors, you can switch, you can control, not switch, you can control servos, you know, standard RC servo, remote control servos. There are some digital inputs. You can use some of these digital inputs for push buttons or for measuring, if you use interrupts to measure, for example, PWM, pulse width or frequencies. There are analog inputs available if you want to measure, for example, battery voltages, or if you want to simulate battery charging circuit and see the curves of charging or discharging curves of batteries. That all works. And of course, just random sensor measurements, which we will have, or which the university will have available. All of the outputs are PWM capable, so can be used for motor control. Okay, next slide, please. There are several sockets for I2C modules. These are commonly available on Amazon, on AliExpress. They contain, for example, inertial measurement sensors, accelerometers, gyroscopes, barometric pressure sensors, temperature sensors. Those are all available, can be plugged in. In this case, the I2C interface was, or the sockets were, we attempted to make them as universal as possible for a large amount of experiments. Next slide, please. This is probably more interesting. There is a socket that is connected to a serial interface, serial UART interface on the microcontroller for reading GPS data. The GPS data of commercial GPS modules, which are also available from various distributors, are usually coming in a serial clear text format, which is based on the NMEA 0183 standard. The course will be talking about that. The socket is somewhat universal. It will fit several different GPS modules for experimentation, including devices with the u-blox Neo 6M, 8M chipset, the Chinese ATGM 336, the Quectel L86 chipsets. So basically, some of these modules are GPS only, some of these modules are GLONASS. And in the description of the NMEA sentences, that's what the text strings are called. An NMEA sentence is basically just a text string. and so that we can, or that your professors can point out the differences between the different GPS modules, so that you can read the data in the most universal way. The characteristics of the typical GPS applications will be briefly covered, but most likely not in detail, simply because there isn't much enough time in the course. But if you are interested, your professors most likely can steer you into the right direction. When I'm saying characteristics of the typical GPS applications, then I mean the GPS will give you the position and a number of other data, for example, the amount of satellites that it sees, the speed that it thinks it runs on, or that it runs at, and of course the time, which is sometimes the sole reason for implementing a GPS. But that is not enough. The typical GPS application is one of four that is either position, tracking, navigating, guidance systems, navigating, or time. For example, position, you will say, okay, I have the position, so what's the big deal here? The problem is that the GPS signal wanders. The accuracy is depending on the satellite strength, depending on the number of satellites that it sees. It might be, even if it has a lock, it might wander around by 2, 3, 5 meters. So every instantaneous position that you're getting is accurate to this amount. If you really want to know your position, you're standing still, you know, and you know that you're standing still, and you know you're not moving, and your GPS is showing you, okay, sometimes from second to another second, it's showing you 2 meters here, 2 meters off there, a meter in the other direction. Then you need to average. And you need to find out how long do you have to average to get the accuracy that you want. So that is a problem for that application. For tracking, the problem is that you get the data. Where do you store the data? Do you need an external memory? Do you need a file system? And then the problem is, how do you get the data to the user? Do you have a wireless interface, or do you have a micro SD card that can be removed? Do you have a user interface, like a screen, that the user can see the data on? That's what basically turns a GPS from just a module into a system. For the navigation, guidance systems, you will have to worry about waypoints. How do you enter waypoints? How do you get to the waypoints? How do you deal with, for example, currents? Like if it's at sea, how do you deal with currents that are moving you off course to compensate for that? That is what makes a module. What's the difference between just a module and just reading the string and having a system? Time, that is often underestimated. Quite often, a GPS module is being implemented solely for getting time. Because what it does, and you might be saying, okay, why would I use a GPS module for that? I can just use a real-time clock. They're cheap, no problem. The problem is setting the clock. Suddenly you need a user interface. Suddenly you need somebody to go to your device and update the time if the clock drifts. A GPS will always give you accurate, extremely accurate time. So if you have, for example, an irrigation system in the middle of nowhere, solar operated, and you want to make sure that this irrigation system turns on is precisely at sunset, for example, then you can do that without using a real-time clock, just by using the GPS as a time source. You will never need to set it. Okay, sorry, that much, or that was a little bit about GPS. Next slide, please. Slide 19, yeah. The course will talk a little bit about the differences between common microcontroller display types and their characteristics and control as well. I probably should start with the off-board bus connectivity. There is an interface for an RS-485 interface. RS-485 is a differential asynchronous bus. If you don't know what that means, no problem. The course will tell you. It also has connectors for access to a microcontroller SPI and I2C buses. The I2C, SPI and I2C buses are synchronous buses, not asynchronous. They are most of the time being used for interfacing modules on the board or very close on the board. They do not have built-in error correction. RS-485 as a differential bus is already hardened against distortions, against interference. Most RS-485 bus implementations will also use packetization and will use a CRC to make the data to basically detect faults or detect issues in the data integrity. LCD, LED displays can be used. You can see here in the little picture. This picture demonstrates the board in its intended enclosure. Most likely in the course, there will be a different enclosure. But if, for example, for experiments outside, if you wanted to take the board outside as part of an experiment, you can put it into an enclosure, and you can take it outside, and it is somewhat protected. You can see here this module with an LCD interface. This LCD interface is connected through the I2C interface. The LCD display, did I say interface? The LCD display is connected through the I2C interface. The RS-485 is an example for an industrial bus interface. Bus characteristics, possible line length, bus speed, and differences between RS-485 and other buses will be mentioned, not in detail, but will be mentioned, as well as examples of RS-485 implementations. One item, for example, is RS-485 can be long. RS-485 can be significantly longer than, for example, Ethernet. Well, the typical Ethernet, the Cat5 Ethernet, which is normally limited to 100 meters. Of course, if you use fiber optics or anything like that, then Ethernet is unlimited. But in an industrial context, it is usually easier to just use a Cat3 cable and RS-485. If you just need a measurement data, some measurement data from a sensor that's 500 meters away, then RS-485 is just simpler to use. Oh yeah, and of course the RS-485 interface would be a typical method for connecting to an embedded PC or a single board computer if you have a system that contains of several of these devices. Okay, next slide, please. There is an audio section. The board was designed to provide some audio interface. This could be used, for example, to test filter algorithms. It could technically be used to connect it to other audio equipment, so for example, a radio, like a two-way radio. One is connected, the DAC output on one of the processor pins can be jumpered over so that it can also be used for a DC digital to analog output, for example, controlling other devices that need a variable DC voltage for controlling them. But otherwise, it can be used for generating sine waves, for generating, for example, DTMF. And the input can be used to implement filters. If you're interested in that, like that is too much really for the introductory embedded systems course. But if you're interested in that, talk to your professor. Next slide, please. Following will be some examples of embedded systems design work from my work history. Next slide, please. Okay, we picked, or your professors picked two examples. One is a little bit older, is a fuel cell control system, but I think it's a good example because it was in the end actually not successful. The control system was successful, but the project was not successful. Okay, next slide, please. Next slide, please. Okay, a manufacturer of thermoelectric generators was developing a residential power generator based on a solid oxide fuel cell. Solid oxide fuel cells are high-temperature devices and operate on natural gas. The suitability for residential application was still being researched by scientists working on the project. Corporate management expected a positive outcome and prepared for volume production. A control system was required. So what's behind this? So first, I probably should talk about thermoelectric generators, which is not the original, which is somewhat unrelated to the project, but related to the company. If anybody knows what thermoelectric generators are, they are, I possibly should explain, they are basically bundles of thermocouples inside a flame. A thermoelectric or a thermocouple is essentially just two pieces of metal which are exploiting an effect that's called the Seebeck effect, which means a very, very tiny voltage is generated if two dissimilar metals have a hot and a cold side, are being connected on both ends, and one end is hot and one end is cold. It is a tiny, tiny voltage, millivolts, 25 millivolts, something in that range. And usually thermocouples are being used to measure temperature. The point here is that because it is metals, it is essentially a sensor that is built entirely from two different metals. You can reach very high temperatures. These thermocouples can measure temperatures at very, very high temperatures. I'm talking a common, super cheap K-type thermocouple can measure up to 1300 degrees Celsius and without breaking. So usually thermocouples are being used to measure temperature by measuring this tiny, tiny voltage that is being generated between both ends, between the hot end and the cold end. Now, somebody figured, okay, what happens if we are putting a whole bunch of these in series and puts them in a flame? So they created a thermoelectric generator by basically bundling up hundreds and hundreds of these junctions, of these two metal junctions, and put them into a flame. The effect here is that there are these generators, and that generates power. Not much, just 50 watts, like 5 watts, 50 watts, like in these maybe up to 500 watts, like generators, maybe up to 500 watts may exist, but generally very low power. But these thermocouples have exceptionally bad efficiency, but they are also exceptionally robust because they have no moving parts. They are literally just metal inside a flame. So these generators can produce power forever. they are usually being used in remote locations where maintenance is essentially very difficult to do, and where there's easy access to a heat source. What does that mean? It means most of the time these are being used to power telemetry equipment on gas pipelines, because there's a gas pipeline, so there is natural gas or propane available, and there is equipment, radio equipment, for example, or satellite equipment, measurement equipment that needs to be powered, that doesn't need much power. These thermoelectric generators, they are ideal for that. Again, terrible efficiency, but exceptional robustness. So this company was approached by, or I don't remember if they were approached or if they looked for this project. They looked at these solid oxide fuel cells, and they thought, we can use this for a similar purpose. There are no moving parts in the fuel cell. It's not a generator. It's not like a gas engine generator. There are no moving parts. They are powered by their high temperature, just like the thermoelectric generators. They run on natural gas. If somebody is asking why natural gas, fuel cells generally run on hydrogen. Well, natural gas is most of the time methane, and methane is CH4. So natural gas mostly contains of hydrogen. The process was absolutely working and possible, but the researchers working on this were trying to make it suitable for residential applications. And a company that was basically a natural gas provider in the province, was also trying to make this technology work so that they can sell more natural gas for electricity generation in remote locations. Yeah. So the bottom line here is the technology was basically where the SOFC technology was and is working, but wasn't mature at the time. The management was thinking, okay, this is great. Let's go for volume production, or let's design a control system that is possible, that can be trimmed down for cheaper volume production. Okay, next slide, please. So this presented the microelectronics department with conflicting requirements. For volume production, a low-cost solution was desired. For technology research, the project scientists, the PhDs, no offense to your professors, engineers and PhDs are sometimes on opposite sides of an issue. The project scientists were asking for a flexible amount of sensors at variable locations, basically because the scientists didn't quite know yet where to look for the ideal points of data. They just wanted to put sensors everywhere, thermocouples everywhere, pressure sensors, gas flow sensors at various locations. I will talk about that. A modular approach was chosen. The control system was implemented as a number of sensor modules based on a microchip PIC18F458. It was an 8-bit microcontroller. This project is over 20 years old, so you will not be able to find the PIC18F458 for sale anymore. However, the follow-up module, the PIC18F4580 with an additional 0, I believe is still available, and it's mostly compatible. This is an indication how long-lived embedded systems, this is just as a side note, just as an indication how long-lived embedded systems can be. In the consumer field, the lifespan of an embedded system, of a product, might just be half a year, 2 years, 3 years. If it comes to the consumer field. In the industrial field, the embedded systems can live 10, 20, 30 years and need to be maintained for this time frame. That was just a side note. So the modules were based on this microcontroller. It was chosen because it was one of the first CAN bus microcontrollers, like a microcontroller with a so-called CAN bus available on the market. The CAN bus was around for like a number of years already, but it was mostly used for larger automotive microcontrollers. And it was connected to a main module using a 16-bit HCS12 freescale microcontroller. Nowadays, you would be using, for a similar purpose, you would be using a single board computer like a Raspberry Pi. There are different ones. I'm always mentioning the Raspberry Pi because it's just this typical example of a single board computer, but there are so many available. Yeah, so I mentioned that the PIC 18F458 was one of the earliest 8-bit CAN microcontrollers. The CAN bus is originally an automotive bus. It has several advantages in this application. It is safe in terms of the data integrity. It has a high amount of data integrity. The bus itself is a differential bus, and the engine that's running the CAN module has CRC protection built in. So if a bit flips, if it is detected that a packet has been corrupted, a new packet or the same packet will be asked for automatically without the microcontroller having to do anything. So by the time the message arrives at the microcontroller for the programmer, you can be assured, or the programmer, the designer can be assured that the data integrity is a given. It is a multi-master bus. So you don't have to worry about implementations of master-slave firmware. The most RS-45 firmware implementations are master-slave buses. There's a main module, and this main module has to organize picking up the data, requesting data, picking up the data. That is an additional step to create a protocol for that, where the CAN bus is by itself a multi-master bus that has its own bus arbitration and is deterministic, which makes it great for cars. Because so when I'm saying bus arbitration, it means that messages can be prioritized, and the higher messages will, in case of a conflict, the higher priority message will get through. And it is deterministic. Basically, you can give each message a priority and decide how delayed it at maximum it can be. If you don't understand any of that, the basic line here is that the CAN bus is very good for real-time tasks and for transferring measurement results. It is very bad at transferring large amounts of data, and for that purpose, USB or Ethernet is much better suited. Okay, next slide, please. The same core, the same processor core was reused. That is also something typical that in this kind of situation, a developer might have to live with, or not live with, but that can be utilized. So both for the hardware designer might be able to basically just copy and paste an entire circuit core, meaning the processor with a programming header, with crystal, with interface chips, or with surrounding interface chips. All of that can be taken basically as one group of components and moved onto different modules. For the software developer, or the firmware developer, it is possible to reuse the same core firmware, which, for example, contains the same routines for running the, in this case, CAN interface, the same routines for running an RS-232 interface for debugging. the same core firmware can be reused for a variety of different modules. There's a list of different modules here that we implemented at the time. One was for K-type thermocouples. In this case, not just one, but like one module had up to 8 per module. Gas flow sensors, I'm mentioning the company here, TSI sensor, also a testament to how long-lived some of these companies are. Again, this project is over 20 years old. The company TSI still exists. They still make gas flow sensors. From what I understand, less for industrial and I think more for medical equipment now. But maybe they still have an industrial gas flow measurement side. Gas pressure, for obvious reasons, stack voltage measurement. The stack voltage measurement module needed to be isolated. That is also not unusual in power applications. Isolation is frequently a requirement. So in order to do this, in older times, you possibly would have used a somewhat analog circuit using a voltage to frequency converter and transfer the voltage into a frequency and then measure the frequency. But in this case, it was the easiest to just to isolate an SPI interface using optocouplers and using an SPI, a separate SPI-controlled A2D converter, which of course had to be powered by an isolated power supply. That is also fairly common. You will frequently see isolated power supplies to be used in this kind of hardware. The DC current sensor was interesting because it was Hall sensor based, because the SOFC, the fuel cell, was outputting DC, not AC. So the typically used AC current transformers could not be used. A separate, similar-looking DC current sensor had to be used, which couldn't be a shunt resistor. How this DC current sensor was implemented in order to avoid the nonlinearities of a Hall sensor was basically in a magnetic core that was surrounding the DC line where the current was being measured. A counter electromagnetic force was generated. The Hall sensor basically just had to verify that the current generated magnetic force was compensated for, and then the measurement of the existence of the DC current was derived from this generated counter electromagnetic force. Sorry, that is probably not actually important. It was just it was an interesting sensor to avoid, to be very linear in the measurement. Valve control, yes, it is kind of also an obvious thing for an application like this, like the gas needed to be controlled, the gas flow needed to be controlled. Stepper motor control. There was also an interesting implementation. You might be asking, okay, how does a stepper motor fit in here? Well, the scientists were experimenting with injecting various types of chemicals to see if they can reduce the stack degradation. The problem is they wanted to be extremely accurate and they wanted to have this liquid extremely dosable. So they chose a medical micropump for this purpose. The problem was that they couldn't use, they wanted to be accurate, so they couldn't use just a standard DC motor. They couldn't use like an unregulated or just a standard brushed or brushless motor. So by using a stepper motor, the RPM, the rotations per minute, could be perfectly determined and set by an additional module. Unfortunately, because they chose a very small micropump, the stepper motor had to run at very, very high speeds and needed to be ramped. That is a topic that will also be mentioned in the course. That is one of the basic software techniques that you might have to encounter, ramping. If it is servo movement, if it is motor movement, you will frequently encounter a situation where you need to ramp. However, for the stepper motor, the additional difficulty was that a stepper motor has resonance points where it will, if you hit exactly this resonance point, you might just fall completely out of step. Meaning the motor will, from rotating at 500 RPMs, within one rotation, drop to 0. And the task then is to avoid these resonance, to step over the resonance points. Okay. At last here is the operator display HMI. The problem here was that for practical implementations, the module, the entire device, the project, needed to be able to run at very low temperatures. We're talking about northern Canada. So a display was needed that could be run at minus 40 degrees. So a standard LCD display would not work at those low temperatures. So in this case, a vacuum fluorescent display, a VFD, was being used, which sounds like a very important device, but in the end, you've all probably seen a vacuum fluorescent display. For example, old VCRs, old video recorders, tended to have these vacuum fluorescent displays. They have like this light blue active shine, or these light blue letters. Very typical. The problem was that a text-based text or graphical vacuum fluorescent display was very expensive, still is very expensive. Like we're talking $80. So this operator display HMI module most likely would have been omitted in the customer version if this product had gone into mass production. Next slide, please. While the control system was functional and in use for system testing and prototype development, in the end, the project was a failure. The SOFC membrane degradation over time was not suitable for residential applications. The technology is still under development, but at the time was not competitive with other forms of power generation. And that was a problem with the solid oxide fuel cell. Still is, I think, since we aren't all using solid oxide fuel cells, but the companies, it still exists, or the technology is still being worked on in various ways. My assumption is that it is still not competitive. This technology is one of these somewhat typical borderline technologies where that just show enough promise of being successful that somebody is willing to invest money to develop it. But in the end, they are not competitive enough to actually replace the previously older forms of power generation, of remote power generation or robust power generation. In this case, the promise of the fuel cell design was, of course, higher efficiency. The fuel cell efficiency was just for the electricity generation in the range between 50 to 60%. And if you, because it was a hot fuel cell, and it was stationary, you could easily use some of the waste heat and, for example, heat a cabin or heat a house with it. In that case, the efficiency would approach almost 100%. Compare that to, for example, a standard power generator, a motor, a diesel engine-based power generator, thermodynamic power generation, or Carnot cycle power generation is usually limited to between 35, even diesel engines, to about 35 to 40% electricity efficiency. Diesel are the better ones, but they're still comparably inefficient. So that was a promise of the technology, but it was running just enough or well enough. It was running just well enough. For example, the membrane degradation, I remember it was estimated it could run for like half a year or almost a year before the degradation was becoming critical. However, for a consumer product, that is a non-starter. You can't tell a consumer that they have to change a significant part, or that they can't incur a significant cost for a product like that every year. It is just not possible. And so, yes, the fuel cell, in the end, the division was being sold off to a different company. Then that different company was being sold off to another different company. They still exist. The company that makes the thermoelectric generator still exists. And they are successful. They are successfully still making thermoelectric generators. But the SOFC technology at this point in time is still under development. And possibly will still be under development for a foreseeable amount of time before it actually becomes competitive. Okay, next slide, please. Environmental data logger with RVT. Yes, this project is a little bit more recent. Okay, next slide, please. A manufacturer of environmental data loggers required an updated version of its existing RVT. In this case, the RVT stands for a radio voice transmitter. They renamed the product later, but at the time it was called the radio voice transmitter. The company's data loggers are rugged and high-value devices designed for use with governmental organizations and weather services. Special purpose application for these data loggers is fire weather prediction and direct support of firefighters in a forest environment. You can see some of these data loggers in those little pictures at the bottom here. They have very rugged connectors. The connectors are actually military connectors. Military connectors from, they are established. They're established connectors. They're not modern, but they're extremely robust. The device also has a touch screen because the people using these devices are generally government workers. Some of them get training, but most of their training is in different fields. Government, well, they are most of the time responsible for example, animal control, or like in the wilderness, of course, not local in a city, for measuring or for basically working in wilderness situations. So the setup and design of these data loggers had to be as simple as possible. And what was chosen for that was a touch screen interface. The connectors are, as I mentioned, very robust, but they are also keyed so that nobody can plug the wrong connector into the wrong receptacle. Starting from the beginning here, a manufacturer of environmental data loggers required an updated version. This is a common task when you get into the industry. So a company has an existing product that is at the end of its production life for various reasons and requires a functional replacement using newer technology. It might be that components are not available anymore. It might be that they have to offer improved features because the competitors are using improved features. But basically, you're not starting from zero. You're starting from an existing design. Okay, next slide, please. For this purpose, a data logger system with sensors and RVT is packaged into a quick deploy station that can be dropped off by a helicopter, usually on a nearby hilltop or mountain summit. Oh, right, I haven't actually talked about the fire weather. This was a specialty of this company that makes these data loggers. Fire weather just indicates how likely a forest fire is. Especially here in Canada, or especially here in British Columbia, where I reside, it is very important to find out how likely it is that a forest fire can start. We have here on roads, for example, we have like those little signs here that show in steps of in 5 different steps in 5 different colors, from green to red, how high the fire danger is. And that is called fire weather. And part of that is a collection of data that these data loggers collect from sensors, which is, for example, the amount of rainfall. It is the fuel moisture. And when I say fuel moisture, I mean wood. I mean basically the branches, broken off branches, broken off trees in a forest that are lying on the forest floor. And it is actually quite funny. These data loggers have a calibrated piece of wood. These stations, they have a calibrated piece of wood pretty much sitting at the bottom where they measure the fuel moisture on. So you can go to a serious, like for example, Campbell Scientific, to a serious measurement manufacturer, measurement device and sensor manufacturer, and you can order, in quotation marks, a calibrated piece of wood for this purpose, for measuring fuel moisture, to predict the likelihood or intensity of forest fires. So this was one of the primary features of this company, of the data loggers, to basically predict forest fires. And in this case, with this device, with this RVT device, to support firefighters. Slide 30, okay. Usually can be dropped off by helicopter. When it says quick deploy, the stations are still fairly heavy. They are not man-portable. They're too big to be put in a backpack, for example. So they would have to be deployed by a helicopter. They're just too heavy to be man-portable. Firefighters can use VHF radios to query for the latest wind direction, wind speed, and temperature conditions using DTMF, and receive a reply in pre-recorded voice samples. This was actually a little bit the background why I put the audio interface onto the lab experiment board, because if you really wanted to, you could replicate this functionality. Firefighters use, because this is usually in remote locations, there's no cell coverage, or there's rarely cell coverage. So they use VHF radios to communicate with each other. These data loggers that are dropped off on these quick deploy stations can be configured to either transmit by themselves under certain alarm conditions, or the data can be retrieved by the firefighter, by each individual firefighter, by entering a DTMF code. DTMF stands for dual tone multiple frequency, and is being used, or this used to be used, in telephones. Everybody most likely has heard DTMF tones before. If you don't know what I mean, if you watch older TV shows, older US TV shows, and you see somebody dialing a telephone, and you hear those weird sounding tones, that is DTMF. The same capability is very often included VHF radios, including those cheap these cheap Chinese VHF radios that you can buy for $50 from AliExpress, or actually probably less from AliExpress. They all do DTMF. So a firefighter could input a number combination, and get the wind conditions, for example, talked to him in a response from this data logger. It is a fairly robotic voice. It is not a very lifelike voice, but it is sufficient to basically get the information that they need. for alerts, if a sudden drop in wind direction happens, the data logger can initiate the transmission and just blurt out basically an alert, 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 wind speed 3.50 miles per hour, and so on, and continue like that. The existing RBT product was based on answering machine technology, and critical components were becoming unavailable. A new version was required. So here's your risk. If you're using off-the-shelf technology that is meant for consumer-grade devices, the risk here is that the product longevity or the component longevity is not guaranteed. Answering machines, or the chips that are on answering machines, are not guaranteed to be available. New models come out all the time, and in this case, the chip was obsolete, and the chip that was recording the voice for the transmissions was becoming obsolete, and yeah, a new version was required. Next slide, please. Okay, because so a new product needed to be designed, the company decided to increase the feature set. So they collaborated with a company, with a data-to-speech company that specialized in generating natural sounding voice from speech samples. They had their own specific algorithm. In reality, what happened, what they did was they were recording the same voice sample, the same speech sample, in different intonations, and were adjusting this depending on the location inside a sentence. So when people ask a question, when people talk, put a word into the middle of a sentence or at the end of a sentence, these words have different intonations, even though they are the same words. And this company was basically storing these words in a number of different intonations, and then was using a proprietary algorithm to assemble the sentences from these samples. This had an important consequence, and that was a lot more storage space was required. There's another thing that I want to mention here. Collaborations like this are fairly typical in the industry. A company that makes data loggers doesn't really want to get involved with creating voice. Like, the first product was created literally by somebody from the company creating the voice samples by speaking them himself or themselves into a microphone. The company decided that for the second product, for the second generation product, that wasn't good enough. And something that a company like this that is specialized in this was bringing to the table is not just the specific algorithm or the different types of intonations. What this company was really bringing to the table was a number of different voice actors. And that was for different languages. And that was really important because the company was trying to become more international and, for example, generate voice samples in Spanish, generate voice samples in French, especially French, because it is a second official language in Canada. This company, the value of this third-party company was not necessarily in their specialized algorithm, in their nicer sounding voice. The value was that they had access to voice actors for different languages, and that they had access to an actual professional studio, like a professional recording studio. So sometimes trying to do everything yourself, like as a company, trying to say, okay, I want to save money, and if a company says, I want to save money and I want to do everything by myself, by ourselves, is sometimes not the right way to go. It can lead to an inferior product. branching out to like another company that has a specialty is perfectly reasonable. Okay, the increased amount of voice samples, which I mentioned, required some implementation of a file system on a NAND flash, which exceeded the capabilities of the previously used 8-bit microcontroller. Here's an issue. So you need large amount of storage. These large amounts of storage are typically used by NAND flashes, as opposed to a NOR flash. Pretty much all mass storage devices use a NAND flash. NAND flashes, like for example, memory sticks. This is an older one, but you can't even really see it. Okay. The problem with NAND flash is that it is interfaced very differently from standard NOR flash. It can develop bad blocks during use. It can lose data when reading. If you read the same location in a NAND flash like 100,000 times, which was part of the testing procedure, basically to read the same voice sample like many, many times continuously for a month, was part of the testing. So some of the NAND flashes can basically lose the data. It is not technically a bad block because it can be overwritten, it can be rewritten, the block is still okay, but the data is lost. So the result of this is that a wear leveling algorithm was required. So not just did the company need a larger memory storage, so it has to use a NAND flash, which is difficult to interface. It also needed to use a more complicated algorithm for wear leveling. This was also beyond the capabilities of like a few developers. So the amount of microcontrollers that were usable for this project were basically limited to Cortex-M devices. Because some of these Cortex-M devices came with a NAND flash interface, and there were applications, libraries available from the manufacturer, it wasn't ST, from the manufacturer for wear leveling algorithms. There was also support available for a file system. In this case, just a simple FAT16 or FAT32 file system. There was also an I2S interface for an external audio DAC. So now we're seeing how the update required the use or made the use of an 8-bit microcontroller unadvisable and required the use of a 32-bit microcontroller. Yeah, so this product was a success. It is still in use, it is still being sold, and it's still on the website for sale under a different name, not as RVT anymore, or RVT2, for implementation into the data loggers. Next slide, please. And I think that is the end of the presentation. No, it is not. Okay. Okay, some more slides are left. ST Microelectronics continues to create new Cortex-M product lines, expands and updates existing lines with new devices and support for new technologies. Yes, they do. ST Microelectronics is actually extremely active in designing new Cortex-M devices. They are, the latest Cortex-M devices are approaching sizes of internal memory of both for flash and RAM, that at some point in time, if they continue like this, at the moment, I think they have the H7 line, at some point in time, it might be possible to implement, for example, stripped down versions of embedded Linux directly into a microcontroller. So far, this has not been possible because embedded Linux just uses too many resources. and it requires an external memory, external ROM memory, or non-volatile memory, external RAM memory. The moment you do that, you're getting into higher power consumption. So for that reason, if you want low power consumption or lowest power consumption, usually microcontrollers without embedded Linux were the only possibility. That might change in the future, depending on how much integration we're getting. The key here is, when I'm mentioning embedded Linux, the key here is that embedded Linux has one big advantage, even if it is not a real-time operating system. So one big advantage is it provides drivers, especially for stuff like TCP/IP, for stuff like USB, especially USB. USB is actually not an easy interface to program for on a microcontroller. USB is complicated. The fine details of USB are complicated. I dare to say, for a microcontroller with an Ethernet interface, it is easier to implement TCP/IP than USB. But luckily, many manufacturers offer libraries for USB support. Okay, the value line products are cost competitive for traditional. Yes, the cheaper, less powerful of their Cortex-M value products are becoming really cheap, like just basically a few dollars. I don't think they have any sub $1 devices, but they certainly, like the Cortex-M0 line, or the M0 Plus line, they are certainly becoming cost competitive with the larger 8-bit microcontrollers. And again, using a 32-bit microcontroller avoids, or can avoid, so many problems that you otherwise would have, so many little traps that an 8-bit microcontroller might present if you're not careful, especially in the interrupt handling. Devices optimized for low power consumption and offer high performance. So there are different lines. ST Microelectronics has different lines. Some, for example, the L4 line, are optimized for low power consumption at the expense of high performance. Other lines, for example, the F, or the F4, the F3, the F4, especially, or the H7 line, have extremely high, some of these have extremely high performance. I'm talking about hundreds of megahertz. STM32 devices with features for functional safety applications are available. This is, I think I talked about that earlier, functional safety, or also called SIL, SIL level. SIL level 4 is actually the highest level. This is an issue. And every manufacturer is usually making devices for this purpose. There are STM32 devices available that come with certifications for functional, or with features. I shouldn't say certification, with features for functional safety. Unfortunately, the really high-level devices, the ones that are meant for example, for automotive, for SIL level 4 applications, are not based on the Cortex-M core, on a Cortex core. I believe they're based on a power architecture core. Those controllers are also available for extremely long life cycles. Some of these processors are available for up to 20 years, which means ST guarantees to a manufacturer, to a product manufacturer, ST guarantees the availability of these devices for 20 years. In our case, for the STM32 line, it's less. I believe there's a number of devices available, of STM32 devices available, with guarantees for 10 years availability. Okay, next slide, please. Active customer support, the data sheets are very good by supplying detailed device documentation, application notes, code samples, development tools, technical support. The data sheets are very good, application notes are very good. And technical support directly depends, of course, how many devices you're generally buying. But the devices, these STM32 devices are extremely accessible for hobbyists, for developers, for everybody, pretty much. Has a large active community. If you have issues, if you have problems, really the question is, in order to solve this problem, is how do you phrase it for Google to get the most relevant responses? And if you manage to phrase it appropriately, to phrase a question appropriately for most problems that you can see, yes, you will get responses. Everybody is using these devices. So this increases speed of development and reduces time to market when designing products. There's another item up for the first point, device documentation, application notes. Also, don't forget about errata sheets. Many microcontrollers or many devices, many electronic or more complicated logic electronic devices have issues in the silicon. It is just something that happens. Pretty much all devices have errata sheets somewhere. Where the application, or not application, where the device steppings are being discussed, what faults are available. So if you encounter a mysterious bug that only happens occasionally, the first thing that you can do is read the errata sheet and make sure that it's not a problem with the silicon, like with the chip itself. It happens, like every processor has errata sheets. Every processor has like little tiny issues that may or may not be important. But yeah, for that reason, good documentation is important. Okay, last point. In general, STM32 embedded systems have bright prospects for the development due to continuous product updates, wide range of applications, active development community, advanced functionality, and support from STM. Yeah, that is a good last sentence. I think now we're at the end of the presentation.
Dear Volker, thank you so much for such comprehensive and interesting presentation. It was really, really brilliant. Thank you so much.
Thank you.
Please, students and all the guests, if you have any questions, please ask. Шановні студенти, будь ласка, питання. Так, за порядком, Олександра, будь ласка.
Yes, good day to you, Mr. Volker. I would like to ask a few questions. First of all, thank you for the presentation. It was very nice. There was a lot of useful information there, but I think I was a bit groggy in the morning when you started the lecture, and some of the points of it were lost on me at the beginning. I would like to ask, how do you determine when to implement the newer technology in development of the software and in implementing new models?
Okay.
Because yeah, I know that there is an issue in reliability where you can't determine whether the newer models will be more reliable than the older ones. In repairability, because you know how to fix the problems that occur in the older models, but not in the new ones. And the compatibility, like in the example that you showed us with the generator that could not compete with its alternatives. How do you determine when to implement the technologies?
Yeah. So in this case, for the example with the generator, I should emphasize that the electronic, the microcontroller modules, the control system implementation was successful. It worked. It was being used by the scientists. What didn't work was basically the technology itself of this solid oxide fuel cell. And I shouldn't say it didn't work, because it did work, but it was just not competitive. And that is an issue that where I don't really have an answer for, because that is kind of outside my field. I'm an engineer. I trust, like, if I get a task to create a product, if I get a task to work with a team to solve a problem, and my assumption is that whoever gives me this task, whoever tells me that, okay, we need this system, we need this, we have to meet these requirements, that those people, which is usually the corporate, the boss, my boss, like the corporate head, the CEO or other people, I just assume that those people know what they're doing. Sometimes they do, sometimes they don't. But basically, if you're talking about when to know what kind of technology outside of the embedded systems makes sense, when to implement this, I don't really have an answer for. If you're asking the question, when do I know what type of embedded system to implement, I can answer that. So what exactly, I might not have fully understood the question.
I was asking when to implement the systems, the new, excuse me. I was asking, how do you know when to implement the newest embedded systems that you develop?
Okay. That is an issue that depends on the problem. So basically, you're being presented with a problem. You work at a company, in this case, as an example, you work at a company, and this company has certain limitations. And you are being presented with a problem. Your boss comes to you and says, we have to create a product for a certain purpose. And you look at this product, you look at the challenge of this product, and then you start thinking about how much time do we have to develop this? What is the cost that is allowed for this product? What kind of development resources do we have? How long do we sell this product for? What is the plan for selling this product for? So there's a whole bunch of items that are going into the decision for the technology. For example, if you're in a team with 3 people, a small team, a very small team, you are going to try to use pre-made modules as much as possible. That, of course, means that the product will become more expensive. Pre-made modules are more expensive. Sometimes a company has a limitation in the amount of components that you can source. So if you look at the newest technology and you say, okay, this microcontroller is perfect for this problem, and you go to the production manager, not your project manager, but the production line manager, and that person says, no, we can't buy this product. It takes too long to order. It is not one of our approved suppliers. Then you can't use this product. You might be forced to use an inferior product. So there's a whole range of different items that go into the decision. What device to use? If you're prototyping, if you're a student, if you want to create a product, if you want to create a prototype of something, you most likely will start with ready-made modules. You want something fast. So you might just go to AliExpress, to DigiKey, to Mouser, which are distributors, and look for pre-made modules. And then you design your hardware around these pre-made modules. If you, on the other hand, want to create 10,000 pieces of this product, a pre-made module would be way too expensive. So you would be looking into a longer development time, but you would be looking into a cost-optimized design. So everything, you might be using BGA packages, which are notoriously hard to prototype with. I don't know if you know a BGA, ball grid array. It means the connections for the chip package is underneath the chip. And you cannot access it easily with multimeters, with oscilloscopes. You have to make test points. So it is more difficult to prototype. But they're cheaper, they're small, and they are normally being used, these packages are normally being used for cost-sensitive devices, for cost-sensitive products. So I can't really give you a clear answer. It completely depends on the product that you're trying to build and the work environment that you're working in.
Okay, thank you. Understood. So that is like situation-based.
It is situation-based, yes.
Okay, thank you.
You're welcome.
Будь ласка, Андрій Лисенко, ваше питання.
Yeah, my question. So first and foremost, I would like to thank you for your amazing presentation. It kept me at the edge of my seat the entire time. And
Thank you.
And I would like to approach this question from a slightly different perspective. So I would like to know more about a career path one's need to take to succeed in the field. So as far as I understand, you come from Germany, right? So, and I would like to know whether you studied in Germany and how did you end up in Canada and the States? Is there anything else that might be useful for someone considering a career in that field?
Yeah. Thank you for the question. So yes, I started in Germany, went to university in Germany, and started my first job in Germany, my first embedded systems jobs, I should say, plural, in Germany. I ended up in Canada because, that's difficult. Well, one, there was a girl involved, but also because at around that time, when I left, there was a special program in Canada for immigrants with software experience because it was the time before Y2K. You might have heard about the Y2K issue. That was before the year, or very shortly before the year 2000. Everybody was panicking under the assumption thus that when the software rolls over, when a timer or timing software rolls over from 1999 to 2000, everything will crash. The world will end. All computer systems will crash, which didn't happen. But because of that, Canada had a specific program for immigrants with software background, with a vastly accelerated time. So I was adventurous. I had met somebody in that long broke up. I had met somebody in actually not in Canada, in the States, but Canada was the easiest way to get to North America. Immigration to the US is virtually impossible. It is very, very difficult. And so I was adventurous. I just took the chance and I came over and I stayed. There's nothing in particular bad in Germany. There is nothing in particular bad in Canada. It's just I got settled here. And I just moved around a bit. I started in Ontario, and moved further west, more and more further west, until I ended up in a province where I couldn't get any further west. So that is my story. For your career path, most likely when you start as a junior engineer after you graduate, if you want to get into the embedded systems field, just be interested. Like that's all really the advice that I could give you. I think I had mentioned in the presentation that you would be in the intersection between hardware design and between high-level programming. And you will most likely need to know a little bit about both. In my case, because of my studying background, I tend to be more on the hardware side. But I would absolutely recommend, be interested in everything surrounding the embedded systems field then, both in high-level and in hardware design, high-level programming and hardware design, but also take upgrade courses. I took kind of like a number of years ago, I took some upgrade courses at a college that was when I was living in Edmonton. At a college for .NET and for database development. And especially the database development course was absolutely amazing, like relational databases. So not for a degree or anything, I just went and signed up for those courses and participated in those courses. I did take the exams, but it was really an eye-opener.
Okay, thank you. And I have a short follow-up question. What would you say are the biggest advantages of working in Canada and the States in comparison with countries like Germany or the Netherlands?
There aren't really. The taxes are reasonably low. Like if you compare it with other countries like Germany, Germany has a very high degree of bureaucracy. Canada, the work in Canada does not pay as much as the US. Like if you are young, you can get a job in the US, take the job in the US. The job in the US will pay a lot more, like a lot more. You will also have a slightly higher cost of living, and you will have problems with healthcare. The US has a terrible healthcare system. However, if you're young and you're still moving around, you want to see stuff, and you have the opportunity for a job in the US, take the job in the US. In general, life in Canada and both in Canada and the US feels freer compared to life in Germany. This is partially a reason of population density. Population density in Germany is very high. There's always somebody who's thinking for you. There's always a government agency who's thinking for you. There's always a person who's trying to stick their noses into your affairs. That is in Germany. It is not bad to live there. But everything is like, this is just my personal perspective. Everything is kind of a bit taken care of for you. It's like living in a padded cotton ball, where both in Canada and the US, people don't really care what you're doing most of the time. There are also some really dumb people around here, especially during COVID. But people can be as dumb as they want. And again, that's just my interpretation here. And you can move far, far greater distances between provinces. You can move thousands of kilometers around. You can see different not just time zones, you can see different climate zones. When I moved from Ontario to Alberta, I drove through, because it was right after 9/11, so I didn't want to drive through the US. They were all crazy about like foreigners. I mean, as in like they were harassing kind of foreigners at the border, so I didn't want to go through that. And so I drove through Canada, from Ontario to Alberta, meaning going north of the Great Lakes, driving. And it was an extremely interesting drive. Just driving through the different climate zones, just right after leaving Ontario, within 50 kilometers, the landscape turned into prairie. And prairie is flat. And somewhere in Saskatchewan, I saw my first tumbleweeds. It was a fairly dry year. I saw my first tumbleweeds, which is like these rolling weeds that are showing up in Western movies. Cowboy movies, which I never thought I would see. Then when you get to Alberta and you get to the Rocky Mountains, that is a totally environment there as well. So one of the advantages of living in a large country with several large provinces is there is a little bit for everything. It is not everything great, but it's interesting. Like when I'm saying not everything is great, I was talking about the healthcare system. In the US, it's very cruel. In Canada, it's overloaded. The cost of living in the big cities here is extremely high. But again, if you want to be alone, yes, you can be alone. If you want to drive 10 hours into the middle of nowhere, into mountains in the middle of nowhere, you can do that. If you want to hike, I go hiking 6, 7, 8 days on hikes on a coast trail, on a mountain trail. You can do that here, which is not possible in Germany.
Okay, I'm sorry. And the last question about the housing crisis. I personally haven't been to Canada, but I have a lot of friends who are staying there for a protracted amount of time. And even though the country is big, as you just described, the actual population is pretty small. Only about 30 million, if I'm not mistaken, right? So, and they're not building enough property, and it's getting really difficult to get rent, especially in big cities where all major tech jobs are concentrated, right? So, did you personally experience that? And just for comparison, say you earn 10K per month in Canada, but you have to spend 5K or even more on housing. But you can live in Germany, say, earn 5K, but spend only 1,000 for housing.
Yeah. Personally, I have not experienced that. However, there is a housing crisis. I was lucky. There is a housing crisis, definitely. Especially the area where I live is insanely expensive. I was lucky enough that I bought the house together with my wife, that we bought the house at a time when the housing prices were still reasonable. And the housing prices have increased. There is definitely a housing crisis coming or active here. Yes, if you're renting, the rents are incredibly high. For a newcomer, I cannot recommend that. Technically, I cannot recommend for somebody to come here, like to Vancouver Island, where I live, because it is just so expensive. The housing situation is just so expensive. For me personally, I was lucky enough that I didn't have that problem because we bought early enough. It is difficult. The cause for this housing crisis, Canada is a big country. Canada has land. Canada also has cheap land. If you go on realtor.ca, you can find 20 acres for $50,000, but far, far away from the big cities. You can find land in the north of BC, for example, just land with nothing but forest on it that you can buy. It doesn't help you if you need to work in a big city. So, and the housing crisis really is partially caused by the amount of immigration. At the moment, Canada has immigration targets of, I believe, between 300,000 to 500,000 people per year on a population of, at the moment, about 40 million people. So the problem is that all the newcomers have to live somewhere. The housing crisis is somewhat self-made. The US doesn't have the same problem because the US doesn't have the same immigration targets. The US has a housing crisis in areas like California, where space is limited, where there is also a very high population density. But if you, for example, try to find a job in the US in the Midwest, Chicago area, in possibly the South, I wouldn't really recommend anybody to go to the South because it is just not great there. But there are places where you can still buy houses for fairly cheap on the salary of an engineer.
Okay, thank you.
Yeah, I hope that wasn't too far flung, or I hope it answered your question somewhat.
Yeah, absolutely. It was perfect.
Yeah. And don't forget, I'm just a single guy here. Other people see the situation differently. But yes, there's definitely a housing crisis going on at the moment.
So please, next question, Sri Sluto.
Yeah, thank you. Thank you very much for the presentation. It was very interesting. And I have the following question about embedded system engineering in general. Like every year, there are more and more people who is willing to become a programmer. And accordingly, the competition in job search is also increasing. And fewer, according to the inflation and a couple of other factors, fewer and fewer companies are willing to hire juniors and trainees in most of programming areas. That's why I'm curious if there is a lot of demand for this specialty for embedded system engineering in the United States or in Canada, for example.
There are a lot of embedded systems around. There are a lot of companies that work with embedded systems around. The problem is they're not always advertising. The problem is it's not always obvious that these companies hire embedded systems developers. It is a problem. Like to your first question, I would have to say that if you're worried about your chances as a programmer in the job market, I would say specialize, like increase your knowledge, specialize in a field that may be embedded systems, it may be something different. Embedded systems has worked for me. It might not work for you, or something else might work for you better. But embedded systems are needed by a lot of companies, even companies where you don't think that they would have embedded systems. The town where I work here has a whole bunch of companies that are making products that use embedded systems, or that are being programmed by embedded systems designers, but it's not quite obvious. There's a company that makes industrial joysticks for forestry equipment. These are being controlled by 8-bit microcontrollers, or these are being scanned by 8-bit microcontrollers, like this displays and everything. There are companies that make, there's a company here that makes environmental control systems for buildings. There are companies that make systems for lighting. There are companies that make systems for traffic lights that use embedded systems. And those are all not necessarily obvious. And your best bet is networking, I think, in general, not just for embedded systems, but in general. Use LinkedIn. Well, LinkedIn is popular here. I don't know what is popular in Ukraine. But if you can network with other students, if you can exchange information with other companies, if you go to trade shows, if you go to fairs like the Electronica in Munich, for example, if you can visit there and you walk around and you hand out business cards, or you're interested, you show interest basically. You send out emails to show interest. The system here is also arranged in a way that students in Canada at least, go through something like what's called co-op terms, which means from the university, they're being sent to companies to gain work experience. So when these students finish their university studies, they already have connections to 2, 3, 4 companies where they can ask for jobs. I don't know if there's something similar in Ukraine available. Most of the time, most of the jobs really are not necessarily advertised, and you have to ask for them, and you have to make connections to the people in companies to find these jobs. That is unfortunately the reality that I've experienced. Go for years, while you're studying, look at the job websites, look at the job market, write down, put links, make a list of companies that at some point in time in the past have put up a job ad for an embedded systems designer. They might be under different names. They might be under embedded systems developer, engineer, firmware designer. There's a bunch of different code words that you can look for. And if you have a list of these companies, then those are the companies after you graduate where you can show interest, where you can just ask. Not the HR people, but possibly directly the engineers. All the engineers, or most of the engineers at those companies will try to help you if you show interest. Like, that is my experience. I've never met an engineer at a company that would try to shut down somebody for fear of competition. Everybody is I shouldn't say having fun, but everybody, or many people, are invested. Engineering, embedded systems, hardware, software. Engineering is not just their job, it's their hobby too. And it's their passion too, with many people in these jobs. And nobody will shut you down if you ask questions. At least that's my opinion.
I see. Thank you very much. And the popping up question, depending on your answer. So how it is usually done, does each company, which, for example, produces some sort of goods, have a department for the development of embedded systems, or there are separate companies that provide this facility, this programming service for other companies?
Both is possible. Many companies have their own departments, have their own embedded systems departments. Other companies are specialized in providing consulting or contract engineering. How should I phrase it? Contract engineering services. Well, yeah, it's just a service. I have worked at one company in Edmonton that was doing this, like providing contract engineering. And it was a very interesting job, primarily because this company was being approached by a number of different companies that, so these companies have a problem. They don't have the resources to attack this problem by themselves. And so they go to this contract engineering company to have this problem solved, to have either a product created or just for help with solving this problem. In Alberta, a lot of the industry there is driven by oil and gas. So a number of these issues were related to the oil and gas industry. It could have been, one item was a device for like a downhole camera where it needed like a little tiny microcontroller activator for like for a camera module with a light that needed to be interfaced to find obstructions inside a borehole. And these companies usually have money because they're oil and gas companies, and they don't care if they have to engage an engineering company to get their problem solved. They just want their problem solved. They don't typically, they weren't haggling around or anything. They basically just come to the engineering company and tell us or told us, like, solve this problem. Other companies are coming to the to the engineering, to the contract engineering companies, and they're extremely price driven. They are very, very conscious about how many hours you spend on their project, because they have to pay for these hours. So that was a disadvantage. The advantage in a contract engineering company is that you get to work on many different projects. The disadvantage is that your time that you're spending on these projects is extremely well tracked, and because the customer has to pay for it. And if you work on a project on non-billable time, your boss will ask you, why did you work on this non-billable? Like, you're losing us money. So both options are possibility.
Thank you very much for the answer.
Hi, thank you for your presentation. It was really interesting and useful. And I'm really interested in testing. And now I want to ask you one question about this. How a quality assurance engineer test embedded systems, and how it works in general? What approaches testers use for this? And maybe you can give some information about this.
That is a good job choice. I'm grinning because as a tester, you would be my natural enemy. Because of course, the testers are trying to find the bugs in the code that the engineers create. Because I'm not a test engineer, I can't really tell you what the exact mechanisms are, how test engineers find these bugs. But I can tell you that some test engineers are extremely good at what they're doing. There's probably information online available how to become a good test engineer. Usually it is exercising inputs, exercising a device in a way that it was never designed to be used. That breaks it. Basically, if you're a test engineer, your task will be to break a device, to try to break a device. Of course, it is also partially to do like the boring parts of testing, which is temperature testing, environmental testing, the rattle tests, like there's all kinds of testing that a product goes through, that has to go through before it becomes an actual sellable product. But if it comes to software testing, some people just have a knack for that. Some people are just, and I don't know how they do it. Some people are just really good at breaking other people's code. The developer knows how he has programmed his code, and he will never try to use whatever user interface there is in a way to break his own code, just because it's just not natural to do that. The tester, on the other hand, he looks at, okay, he asks the developer, how are you supposed to use this code? The developer will tell him, okay, you have to use this code this way. And then the tester tries the opposite and breaks the code. And again, I can't really tell you how to do this because I'm not a test engineer myself, but it is a specialty that is valuable to have. It is actually an extremely valuable specialty. There are probably other there's probably more information, other sources of information on the internet about how to become a good test engineer.
Oh, thank you so much.
Yeah, so sorry if I couldn't help really much with the
Yeah,
question.
it's normal, but just I was interested in it, and it's okay. Don't worry.
Please, next question, Mikhaila Shilenko.
Yes. First of all, thanks for presentation. It was very interesting and informative. And I have a question. Where can I find more information about the course that was mentioned in the presentation?
Sorry, I didn't understand that word. More information about what?
About course.
Oh, about the course.
Yes.
Actually, the course isn't quite finalized yet. Your professors are still working on the actual on the proper implementation of the course content. So at the moment, the documentation for the course is not available to the students. Professor Kovalenko, I don't know when at least an outline will be available. Should that be basically the next most urgent item to create a course outline? Like,
yes, Mr. Rademacher, I'll explain the students later, but in general, the students will have a dedicated course devoted to microprocessors and embedded systems. As for now, we see it like a 3-semester long, and this it will be material of the last third semester, because first 2 semesters will be like introduction in different types of microcontrollers, like general information and so on. So we will provide the students with the full insight a bit later.
okay.
Thank you. Please, if there are any questions, you may feel free to ask Mr. Rademacher or me. Please, Mikhail Hunko.
Yeah, thank you for interesting speech. And I want to ask, a few years ago in Ukraine, it was a really big problem to find an embedded specialist, because it's so big sphere. And if, for example, for front end or back end, we can have up to 10, 15 people for one vacancy, and for embedded it was less than 1 people for vacancy, and it was really hard to find specialist. How it works now in Canada, and how it's if we talk about how hard to find a specialist in embedded, is it hard to know?
You mean, so you're approaching it from the other side. You're basically approaching it from the side of a company. You're asking, like, is it hard for a company to find an embedded system specialist?
Yeah, in terms of company. Yeah.
Okay. Which it is, from what I understand, I don't have any contact to any HR department at the moment. But from what I understand, it is somewhat difficult to find to find specialists in general, to find embedded system specialists. It's not that they are not around. The problem is that in the area where I live, the cost of housing is very expensive. So companies rely on the labor pool that already exists, because not many people want to move to a city, be it Vancouver or Victoria or other cities or Toronto. Many people don't want to move to a city where they can't rent an apartment at normal prices, or where they have to share an apartment to be able to afford it. And that is artificially limiting the labor pool for companies here at the moment. That is my understanding of the issue. There are still a number of applicants for every job ad, but it is definitely not that for one job ad that there are hundreds of people applying. And again, the reason for that is the housing situation, which is fairly specific to Canada. Like, I do not assume that Ukraine, for example, or the surrounding European states, that they would have a housing problem.
Thank you, understand.
Please, next question, Alexei Lizunov.
So to begin with, I would like to thank you for your lecture, and my question is, have you ever had an experience in Web3, and if not, what do you think about this way of engineering?
Sorry, experience in web?
Web3, like blockchain, cryptocurrency.
No, I do not.
Okay.
Simple answer, don't have experience in it.
Please, if you have other question, please ask. I see no raised hands, so I suppose no questions more. So I would like to say a very, very big thank you to Mr. Rademacher for such interesting and I'd say brilliant lecture. It was very interesting. It was very useful. Thank you very much. So
Thank you.
For today lecture is finished. If somebody wants to say something, please, student. In general, I see many of reactions. So thank you so much, Mr. Rademacher. It was really, really interesting and useful. Thank you so much.
Thank you for your kind words.
Yeah, thanks for the lecture. Goodbye.
So,
Okay.
Goodbye. Thank you to all. Big thank you.
Bye. Have a nice day.
Good night.
Goodbye and have a good night, Mr. Rademacher.
Okay, bye.
Goodbye.
Goodbye, see you.
Thanks a lot. Have a good day.
Thank you very much. Goodbye.
Bye.